Welcome to another Avaya technology session. This one will be about FabricConnect and its impact on Hadoop HDFS Big Data Server Farms. I'm Ed Kohler, and I will be your host for this session. So what is Hadoop? Well, it's quietly taking the world by storm. Hadoop is focused on parallel compute and storage. Its foundations are in a series of Google white papers that describe a system that leverages everyday compute infrastructures in parallel. Hadoop HDFS is an open-sourced outgrowth through Apache of the Google File System, or GFS. With a few minor differences, the concepts and systems are very similar. There are two other sections to Hadoop. MapReduce provides a utility programming environment that we will go into a little more later. Additionally, Bigtable, or HBase, provides for the representation of structured data within the HDFS environment. The main point is that HDFS leverages on a distributed data footprint rather than a singular SAN environment. Very often, HDFS farms are comprised completely of direct attached storage systems that are tightly coupled over the data center network. Hadoop is available in an open source context, as well as by pure-play vendors such as Cloudera and RMAP. Additionally, it is also available through the offerings of enterprise vendors such as Hortonworks, IBM, Microsoft, and EMC. The main benefit of Hadoop is that it minimizes the need for huge monolithic compute storage infrastructures to support big data or data science analytics. Because it leverages on a distributed node-based data store, most HDFS farms tend to be comprised of DAS, or direct attached storage systems. So big does not have to be big. Hadoop HDFS is more so a scale-out type of architecture that allows for a relatively low-cost point of entry but can grow to accommodate the very large environments. As an example, both Facebook and Google utilize Hadoop or Hadoop-type architecture to leverage huge stores of data for various business purposes. This is because not only does Hadoop offer distributed storage, but it also optimizes file write and read time by the use of metadata. These are very key characteristics that lend well to the highly parallel analytic processes of MapReduce and Yarn, which we will cover a bit briefly later. What HDFS means to Avaya is multifold. The use of large-scale data analytics is quite obviously beneficial to contact center scenarios, where information key to customer trends can be correlated and provided to operators. Business analytics can help in informed decision-making against a relatively accurate historical background trend, rather than using pure intuition. In this presentation, however, we are concerned with the way HDFS behaves at the network level. HDFS leverages front-end network paths, such as those that are provided by normal Ethernet interfaces. SANs can still play a role, but their importance is greatly lessened, and some say HDFS is better without any SAN systems in the cluster whatsoever. Another important point is that HDFS uses pipeline writes and ordered reads throughout the cluster. Some upcoming slides will clarify what this means. But at this point, it is important to note that HDFS benefits by large, low-latency east-west pipes. This fits well with much of the development activity that Avaya has been placing within the data center top-of-rack switching environment. In data analytics, a lot of data has to be read very fast. The longer the read time, the longer the overall analytics process. HDFS leverages parallel processing at a very low level to provide for a highly optimized read time environment. In this slide, we show the same 1 terabyte file being read by a conventional serial read process versus a Hadoop HDFS cluster, which optimizes the read time by an order of 10. Note that the same type of system is being used in both instances, but in the HDFS scenario, there is just a lot more of them. Importantly, actual analytics programming can run in parallel as well. This means that relatively large amounts of data can be processed with a somewhat modest infrastructure investment. As an additional note, HDFS also provides for redundancy and resiliency by the use of replication of the distributed blocks within the cluster. The components of HDFS are fairly straightforward and shown in a simplifying form on this slide. The overall HDFS cluster is managed by an entity known as the name node. You can think of it as a library card index for the file system. More properly, it generates and manages the metadata for the HDFS cluster. As a file gets broken into blocks and placed into HDFS, it's the name node that indicates where, and the name node that tracks and replicates if required. The metadata always provides a consistent map of the distributed file system as to where a specific piece of data resides. This is not only for writing into, but also extracting out of the cluster, but also for the data analytics, which requires the reading of the data for its execution. It is important to note that in first-generation Hadoop, it was a single point of failure. The secondary name node in Generation 1 Hadoop is actually a housekeeper process that extracts the node name runtime data and copies it to disk, where it is known as a name node checkpoint. Recent versions of Hadoop now offer redundancy for the name node process. Cloudera, for instance, provides high availability for the name node service. There is a second node known as the job tracker. This service tracks various jobs required to maintain and run over the HDFS environment. Both of these nodes are master role nodes. As such, Hadoop is not a peer-to-peer clustering technology, but more so hierarchical. In the slave role, there are data nodes. These are nodes that actually hold the data that resides within the HDFS cluster. In other words, the blocks of data that are mapped by the name node reside within these systems' disks. Most often, data nodes are direct attached storage and only leverage SAN to a very limited extent. The task tracker is a process that runs on the data nodes and are managed and report back to the job tracker for various executions that are to occur within the Hadoop HDFS cluster. And lastly, one of these nodes is referred to as an edge node, which will have an external interface that allows for the HDFS environment to be exposed so the PCs running the Hadoop HDFS client can be provided access. The next series of slides will highlight these roles in more detail. HDFS is actually fairly efficient in that it incorporates replication into the process of writing. When a file is ingested into the cluster, it is broken up into a series of blocks, as shown on this slide. The name node utilizes a distribution algorithm to accomplish the mapping of where the actual blocks will reside within the cluster. A HDFS cluster will have a default replication factor of 3. This means that individual blocks will be replicated 3 times and then placed algorithmically. If a data node were to fail within the cluster, HDFS will respawn the lost data to meet the distribution and replication requirements. All of this means east-west data, but it also means consistent distribution and replication, which is critical for parallel processing. HDFS is also rack aware. By this we mean that the name node can be programmed to recognize that certain data nodes are common to racks and consequently should be taken into consideration during the block distribution or replication process. This awareness is not automatic, however. It must be programmed by batch or Python script. However, once it is done, it allows the span algorithm to place the first data block on a certain rack, and then placing the 2 replicated blocks into a separate common rack. As shown in the slide, data blocks A and B are distributed evenly across the cluster racks. Note that while the default factor for replication is 3, HDFS can be increased or decreased at the system, at the directory, or even the file level. As adjustment to the R factor is done for a certain data set, the name node assures that data is replicated, spawned, or deleted according to that adjusted value. HDFS uses pipeline writes to move data blocks into the cluster. In the slide example, an HDFS client executes a write for file.txt. As an example, the user might use the copy from local command. The request is sent to the name node. The name node responds with a series of metadata, telling the client where to write the data blocks. Data node 1 is the first in the pipeline, so it receives the request and sends a ready request to data nodes 7 and 9. Nodes 7 and 9 respond, and then the write process begins by placing the data block on data node 1, where it is then pipelined or replicated to data nodes 7 and 9. The write process is not complete until all data nodes respond with the write process. Note that the write process for the other blocks is happening in parallel to this. Note also that most data center topologies utilize a spine and leaf type topology, meaning that most of the rack-to-rack data distribution must flow up through the data center core nodes. In Avaya's view, this is highly inefficient and can lead to significant bottlenecks that will limit the parallelization capabilities of Hadoop. Avaya has been focusing on this east-west traffic capacity issue within the data center top-of-rack environment. Reads within the HDFS environment happen in a similar fashion. When the Hadoop client requests to read a given file, the name node will respond with the appropriate metadata so that the client can in turn request the separate data blocks from the HDFS cluster. It is important to note that the metadata for a given block is in an ordered list. In this slide, the name node responds with metadata for data block A being on nodes 1, 7, and 9. The client will request the block from the first data node on the list. Only after a failed response will it attempt to read from the other data nodes. An important point to note is that the read requests for block B and C happen and occur in parallel. It is only after all data blocks have been confirmed for the file and that the transaction has been completely acknowledged that a read request is deemed complete. Finally, similar to the write process, any rack-to-rack east-west flows need to flow over the core switch in a typical spine-leaf architecture. We at Avaya have anticipated this change of data center traffic patterns. As such, we have taken a much more straightforward approach. We call it distributed top-of-rack, or DTOR. Top-of-rack switches are directly interconnected using very high bandwidth backplane connections. These 40 gig plus connections provide ultra-low latency direct connections to other top-of-rack switches to address the expected growth. The DTORs are also connected to upstream core switches, which can allow for the use of L3 and IPDPN services to ensure security and privacy. Note that the DTOR approach is much better suited to the high-capacity east-west data flows rack-to-rack within the data center. Going further, by using front port capacity, direct east-west interconnects between remote data centers can be created. We refer to this as remote rack-to-rack. One of the unseen advantages of DTOR is the reduction of north-south traffic. Where many architects were looking at upgrading to 40 or even 100 gig uplinks, Avaya's approach negates this requirement by allowing native L2 east-west server traffic to stay at the rack level. This provides for relief to these strained connections. Another key advantage of DTOR is the flexibility it provides. Server-to-server connections in rack across rows, building to building, or even site to site. The architecture is far superior to other approaches in supporting advanced clustering technologies such as Hadoop HDFS. Traffic stays where it needs to be, reserving the north-south links for end-user traffic or for advanced L3 services. Only traffic that classifies as such needs to traverse the north-south paths. The end result is a vast reduction in the traffic on those pipes, as well as a significant performance increase for the east-west data flows. The key to any successful architecture model is to tick as many requirements boxes as possible. Scalability and flexibility are two components in this. Avaya's Fabric Connect provides for these key attributes and more, being flexible to address anything from the small to the large while providing all the key benefits is unique to our architecture. This provides for a significant growth path without the need to overhaul or redesign the network as it grows. Scaling from 10 to thousands is another quality unique to Fabric Connect. Let's take a look at how. Avaya's DTOR can operate in two different ways. Stack mode can connect up to 8 DTOR switches. The interconnect is 640 gigabits without losing any front ports. Additionally, dual TOR switches can be used to scale up to 16, giving a maximum east-west traffic profile of up to 10 terabits per second. Fabric mode creates a one-hop mesh, which can scale up to hundreds of DTOR switches, and port counts tops out at 10,000 plus 10 gig ports, with a maximum east-west capacity of up to hundreds of terabits. No other vendor can come close to this degree of scale, and this is just within the rack-to-rack environment within the single data center. Avaya's DTOR solution can scale in either mode, whether your needs are small, large, or unknown. DTOR and Fabric Connect provides for unmatched scale and flexibility, perhaps most importantly, the capability to solve your challenges, even the unknown ones that most of us face, particularly with data science analytics. As the HDFS farm grows, seamless expansion capability of Avaya's DTOR environment can accommodate it without major architectural design changes. Another key benefit is that Avaya has solved the complex PCI or HIPAA compliance issues without having to physically segment or by adding layers and layers of firewalls. The same can be said for any sensitive data environments that might be using Hadoop, such as patient medical records, banking, financial information, smart power grid management, private personal data. Any of these fit the profile. Avaya's stealth networking technology can keep such networks invisible and self-enclosed. As a result, any attack or scanning surfaces to the data analytics network are removed. The Avaya Virtual Services Platform 7000 is ideally suited to delivering today's pressing need for flexible, high-speed Ethernet connectivity in the high-speed data center top-of-rack role. Additionally, it provides a cost-effective 10 gigabit fan-out capability for existing core switch deployments and also has an application in the campus distribution layer, delivering flexible connectivity and consolidation options. In addition to the versatility offered by the integrated MDA, the BSP 7000 boasts a host of strategic innovations that will ensure it continue to deliver cutting-edge performance and services throughout an extended life cycle. In addition, Avaya's DTOR environment incorporates the use of an enhanced implementation of IEEE 802.1 shortest path bridging, we call Fabric Connect. By merging DTOR and Fabric Connect in a single platform environment, an end-to-end solution is created that is transparent to the physical layer. As a result, a flexible approach to designing L3 services can be obtained. Rather than routing because you need to, things shift to routing where you want to. With L3 and IPVPN services fully virtualized in the core, the ultimate design flexibility can be offered. These L3 services can be incorporated into geo-redundancy for multiple geographically distributed data centers. Additionally, Fabric Connect can effectively allow for extended L2 east-west flows by the use of remote rack-to-rack directly between these data centers. IPVPNs and the use of L3 VSNs can provide for the use of multi-tenancy, as well as regulatory privacy and compliance. As such, a complete set of network services can be provided for in a superior fashion in a simple two-tier design, the top-of-rack environment and the core. One of the strong differentiating characteristics about Fabric Connect is its immense geographic reach. Other Fabric approaches are typically limited to very small deployments that span within the data center. Fabric Connect also provides for very deterministic forwarding behavior across the SBB network. These two factors combine for allowing long-distance rack-to-rack interconnects between the data centers. This unique capability allows for the direct scaling of L2 east-west capacity that can easily accommodate an expanding but distributed HDFS footprint. All north-south paths are then relegated to purely end-user or proper L3 services. The end result is the ability to scale up and out, and such scaling is transparent to Hadoop. This slide shows how DTOR remote rack-to-rack interconnect works. Note that L2 networks are encompassed under the red VRFs and the corresponding L3 virtual service network. As a result, the whole HDFS cluster is encompassed in a private, self-contained network that we refer to as a stealth network topology. This allows for the use of sensitive data for analytics without undue risk to the information, particularly if stealth practices are diligently followed and the environment is totally closed. The logic of the shortest path bridging will always use the shortest path available for layer 2 east-west traffic. This feature offers vast scaling capability of the traditional L2 domains. Also, if the rack-to-rack interconnects were all to fail, which is extremely unlikely, alternate paths would be available across the core network, and the traffic would still be securely within the stealth network service. Let's take another view. This slide illustrates a comparison of Avaya's stack mode interconnect with other major TOR switch vendors in the industry. It's obvious that Avaya has been anticipating this major shift in the data center traffic movement. A major point is that with stack mode interconnect capability, this is offered for even smaller deployments. To be fair, the graph does a comparison with this mode. But note that with fabric mode interconnect, Avaya's DTOR solution can scale to the largest of east-west traffic capacity demands. Adding in remote rack-to-rack provides for the ability to extend massive geo-distributed bandwidth that can scale out to terabits. Now that we have the data effectively stored and retrievable, we want to exercise certain queries against the data, and hopefully receive meaningful answers. MapReduce is the original methodology documented in the Google white papers. Note that it is also a utility within HDFS and is used to chunk and create metadata for the stored information within the HDFS environment. Data can also be analyzed with MapReduce to extract meaningful secondary data, such as hit counts and trends, which can serve as the foundation for predictive analysis. This slide shows a MapReduce project being sent into the HDFS environment. The HDFS cluster runs the MapReduce program against the dataset and provides a response back to the client. Recall that HDFS leverages parallel read-write paths. MapReduce builds on this foundation. As a result, east-west capacity and latency are of importance to the overall consideration and overall performance of the solution. Avaya's DTOR solution provides for easy, consistent scaling of the rack-to-rack environment as the Hadoop farm grows. The components of MapReduce are relatively simple. First, there is the map function, which provides for the metadata context within the cluster. So there is an independent record transformation that is the representation of the actual data that is stored. This includes deletions, replications to the system. For analytics, the function is performed against key-value pairs. The best way to describe it is to give an example. Let's say a word, and we want to see how often that word appears in a document or a given set of documents. Let's say that we are looking for the word cow. This becomes the key. Every time MapReduce function sees the word cow, it ticks a value of 1. As the function proceeds through the various read, ticks are appended to a list of key-value pairs, such as cow 31, or there are 31 instances of the word cow in the document. For this type of job, the reduce function is a method to aggregate the results from the map phase and provide a list of key-value pairs that are to be construed as the answer to the query. Finally, there is the framework function, which is responsible for the scheduling and rerunning of tasks. It also provides for all utility functions, such as providing a split to the input, which becomes more apparent on the next slide, but it is actually referring to the chunking functionality that we spoke of earlier as data is written into HDFS. Typically, these queries are constructed into a larger framework. The next slide shows a simple example of a query framework. Here we see a simple word count histogram, which is the exact process we talked about on the previous slide. In the upper arrow shows the actual data flow across the MapReduce process chain. As data is ingested into the HDFS cluster, it is chunked into blocks as previously covered. The map function makes this read against the individual data blocks. For purposes of optimization, there are copy, sort, and merge functions which provide for the ability to aggregate the resulting lists of key-value pairs. This is referred to as the shuffle phase and is accomplished by leveraging on east-west capacity within the data center. From this reduce function, reduced received key-value outputs in a single statement, such as cow 31. In the example above, we show a construct to count for 3 words: cow, barn, and field. The details for the 2 key values is shown. The third is simply an extension of that which is already shown on the slide. From this, we can infer that among these records, cow appears with field more than barn. This is obviously a very simple example with no real practical purpose unless you are analyzing dairy farmer diaries. But it illustrates the potential of the clustering approach in facilitating data farms, which are well suited to the process of analytics, which leverage very heavily on read performance. As one might guess, things could very quickly get unwieldy, dealing with large numbers of atomic key-value queries. YARN, which stands for Yet Another Resource Nanny, allows for the building of complex tasks that are represented and managed by application masters. The application master starts and recycles tasks and also requests resources from the YARN resource manager. As a result, a cycling, self-managing job could be run. Weave is an additional overlay that provides more management functions. This slide illustrates a practical, functional use of the technology. Here we are monitoring incoming flagged credit card transactions. Transaction data may be flagged key-value pairs. Indeed, there may be dozens of key-value pairs that are part of this initial operation. This provides for the consistent input into the rest of the flow. LDA scoring, based on latent Dirichlet allocation, allows for a comparative function against the normative set. It can also provide a predictive role. In this step, provides a scoring function on the generated key-value pairs. At this point, LDA provides for a percentile of anomaly to a given transaction. From there, further logic can then impact a given merchant score. All of this is based on yet another higher-level construct known as Mahout. Mahout provides for an orchestration and API library that can provide and execute a wide variety of operations, such as LDA. Examples are matrix factorization, k-means, fuzzy k-means, logic regression, naive Bayes, and random forest, all of which in essence are packaged algorithmic functions that can be provided against the resident data set for analytic and/or predictive purposes. Further, these can be cycled, such as the above example, which would operate on each fresh batch presented to it. The end result is a very powerful environment that is capable of machine learning type phenomena. The best part of it is that it is accomplished with off-the-shelf technologies. No supercomputer is required, just a solid distribution storage compute framework and superior east-west traffic capacity. In summary, Hadoop HDFS is a lower-level data-distributed store that heavily leverages on MapReduce functions to generate and exercise detailed metadata maps of the actual data within the system. MapReduce, YARN, and Weave, and extended environments such as Mahout can perform varying degrees of analytic functions against the data repository, from basic word count exercises to full-scale machine learning environments. Example use cases for the technology include grepping of data sets, log and statistical analysis, simulations, sort and merge, inverted web graphs, and full machine learning. We at Avaya have anticipated this trend and have recognized for quite some time the change that is occurring within the data center. Avaya's DTOR solution and FabricConnect solve the east-west traffic capacity issue and allow for growth from the very small to the very large in a seamless fashion. Legacy protocols and consequent design limitations are totally removed. FabricConnect DTOR is the ideal switch fabric for Hadoop HDFS environments. Remote Rack to Rack provides for the ability to extend this capability in a geographically distributed method for resiliency and protection of the data footprint. Additional benefits are the improvement of business continuance and compliance for sensitive or private data farms. The ability to cover all of this in a single architecture is a testament to the work that has been done here at Avaya in anticipation of these drastic upcoming trends that are upon us within the data center. Avaya's FabricConnect for the data center is ready.